guys, Dr. Betts here coming out with another fantastic chemistry video, and today we're going to talk about carbohydrates. As you all know, we're on shutdown because of the coronavirus, so I, your illustrious lab partner, am going to do all the wet chemistry that you were supposed to do if only we could get you in the lab. I'm going to do the wet work for you, you're going to be the intelligent chemist, and you're going to figure out the results on your own. This is in lieu of being here. We're doing our best for you guys. I hope you guys will work with us and do your best as well. It's important that you still learn this stuff because it's still very important as you move forward in your future careers. So now, let's get after it. And now I'm showing you the dry part of the lab where you just have to look at some models and essentially draw what you see. Because you can't be in the lab to see the models, I'm going to have to basically present them as still photographs, unfortunately, and then kind of draw them for you, trying to point out things along the way. It's not the ideal situation, obviously, because this is where we're at with this virus, but this is what we're going to do, okay? So now just please bear with me, work with me, and we'll get it done. Now, as you can see here, we're looking at a molecule of glucose here and another molecule of glucose here. So I'm up here, guys, in case you're wondering where I am. So we're going to have two glucose molecules come together. And what I want you to do is I want you to draw these glucose molecules in your book. Now I'm going to draw them right now. You just draw what I'm drawing, okay? Now, let's take a look here. Here we have an oxygen back here, which is bonded to a carbon, which is bonded to another carbon, which is bonded to a carbon, to another carbon, and then there's a carbon back here. I know it's difficult to see from the photograph, or somewhat difficult, but there's 1, 2, 3, 4, 5, 6 atoms in a cyclical or cyclical conformation. So let's just draw that. Carbon to oxygen to carbon to carbon to carbon to carbon, and then they're bonded together. So there's my 6 atoms in a circle. 1, 2, 3, 4, 5, 6. Okay. So there's my 6 atoms in a circle. 1, 2, 3, 4, 5, 6. This carbon here has a carbon OH coming off the back. I know it's hard to see, but there's a CH2OH coming off here. This oxygen here is bonded to that carbon. This is your anomeric carbon, so it's this carbon here. Now I'm not showing you whether these OHs are up or down. I'm just drawing them in. I'm just drawing them in because it makes our life a little bit easier. There's a hydrogen here, and there's an OH there, and a hydrogen here, and an OH there, and a hydrogen there, and an OH here, and a hydrogen there. And essentially, this molecule here is exactly the same. So let's just draw that. All right, and then there's a CH2OH off of here. All right, so essentially these two things are exactly the same. So I'm just drawing them pretty much exactly the same. Again, I'm not really worried about the up or downs of these OHs in this class. It's not really that important for you guys in this class. Now, in the disaccharide, I'm going to be a little bit more concerned with the up or down of the glycosidic bond. So now, we're going to draw D-maltose, and here's a structure of D-maltose. Here's my 6-membered ring. 1, 2, 3, 4, 5, 6. Here's the glycosidic bond right here. And here's the other 6-membered ring. 1, 2, 3, 4, 5, 6. Okay? So again, 1, 2, 3, 4, 5, 6 atoms in a ring. Glycosidic bond, there's the anomeric carbon. 1, 2, 3, 4, 5, 6, and there it is. There's the glycosidic bond. I'm kind of using my laser pointer here to really drive home what I want you to look at. Right there, this glycosidic bond. So we'll draw that. It's going to look a little bit complicated, but it's not that bad, really. Now this O is going down. Notice I drew it in the downward direction. There we go. And again, there's other things on these carbons. Now, these hydrogens I just drew have to be up, okay? Because this oxygen is down. These two hydrogens must be up because this is an alpha glycosidic bond. Okay? It's an alpha, oops, you can't see that word bond, can you? There you go. It's an alpha glycosidic bond. So let me just finish drawing in the accompanying OHs and Hs. If I'm going too fast, you just pause the video so you can draw them in yourself. There we go. All right, so there's that one. Now again, beauty of YouTube, you can pause the video right now and watch this part again if you didn't get it. But I think I did a pretty good job. Let me just put it, I messed the hydrogen up here, guys. Sorry about that. All right, next. Now we're getting a lot more complicated. Now this is basically impossible for you to see without me just guiding you through it. What we have right here, this is a glucose molecule. What we have right here, this is another glucose molecule. And this right here is a third glucose molecule. Okay? It's impossible to see on this picture, really. It's not impossible, but it's very difficult. I know what I'm looking for, so I can see it. I want to focus your attention here. That's the glycosidic bond attaching these two sugars. Notice how it's going down. That's an alpha glycosidic bond. Here's another glycosidic bond over here. It's going down. So this is the portion of the polymer amylose. Amylose is a polymer of glucose. But in the polymer, all the glycosidic bonds are alpha. That's amylose. So I'm going to draw this, but I'm going to draw it as a skeletal formula just because it's so much easier. And I think you'll be appreciative of it because it's so much neater. The maltose I kind of drew as a, I kind of drew the maltose as a expanded formula, just kind of drive home the point. But with these big polymers, I like to draw them as skeletal formulas simply because it makes your life a whole lot easier. Now at this point, the polymer will continue. And the polymer will continue. The polymer will just keep going from left to right. And of course, we have to draw on our accompanying stuff. And it doesn't really matter what these H's and OH's are, just make sure they're in. Oops. I'm not going to judge you guys on it, and I'm not even being all that careful with it right now because of the urge and the necessity to get this done because we all have lots of things we have to accomplish before the end of the week. But you get the idea. This is a polymer of glucose. This is amylose. How do I know? First of all, it's not branching. Second of all the glycosidic bonds are alpha. That's how I know. All right, onward. Here is cellulose. Now, again, it's difficult to see from this photograph. I'm going to walk you through it. Here's a glucose molecule here. Here's another glucose molecule here. And here's another glucose molecule here. So this is a portion of cellulose. And again, I'm just going to point out the glycosidic bond. Notice how it is going in an upward direction. So the glycosidic bond is actually beta. Cellulose is a polymer of glucose in which all the not all, but a lot of the glycosidic bonds are beta. Sometimes there's a few alpha mixed in, but some of them are beta for sure. So let me just draw that as a skeletal formula again, just because it's neater. But remember, cellulose is indeed glucose. It's made of glucose. It's just that the glycosidic bonds, some of them at least, are beta. And I'm just, in this polymer, we just kind of drew them all beta just to drive home the point. All right. And let's just draw in some of the accompanying things. Notice I drew all the glycosidic bonds in the upward direction to clearly indicate this bad boy is beta. And again, where you put all the accompanying stuff is not really that important in this class. It is important, absolutely, in reality, but in this class, I don't get too crazy about it because it's challenging to know and to remember, and it really doesn't mean anything unless you've taken some organic chemistry. We could tell you, but it wouldn't mean much to you. There you go. So that's what it looks like. Now, I get it, guys. This is crazy. These models are set up in the lab. Normally, students would have the chance to pick them up, look at them, examine them closely, ask questions about them. But unfortunately, because of the shutdown, this is what I decided to do to kind of help you all. But don't fret. If you have any questions, I'll be around for office hours during the scheduled times next week on Skype. So go ahead and give me a Skype call or hit me up on Skype, whatever you need to do. But let's work together. Let's get through this situation, and I think we're going to come out stronger on the other end. All right, guys. Thanks for your attention. With that, I want to wish you good luck and good chemistry.
Now we're going to do the Benedicts test for reducing sugars of carbohydrates. Here I have some test tubes. One test tube has glucose, one has sucrose. And I'm going to add a little bit of the Benedicts solution to each one. There you go. Let me see if I can get that to the camera for you. There you go. Benedicts reagent to each one. So let me get my goggles on just in case. How much Benedicts solution do we need? About 1 milliliter of Benedicts solution. All right. So here we go. There we go. It's a little tight. And we get 1 mil. That's about it. There's 1 mil. So I'll put 1 mil in with the glucose. There we go. Put it in the heat. Now I'm going to warm this bath. Is warming up now. I want it to kind of get close to boiling, if not boiling. We may see the result before boil, though. Let's keep that in mind. All right. There. Now we're just going to let them sit in the solution. This one here is glucose. This one here is sucrose. All right. So now we just sit and we wait for something to happen. And I think if you look, you can already see something is definitely happening with the glucose. It's starting to change color. Let's give it a little more time, a little more energy in the heater. See what happens. But you can already see definitely something is occurring with the glucose solution, not the sucrose solution though, so that's interesting. We're going to let that go for a few more minutes. Okay guys, I think that we can call it right now. You can see the glucose solution has definitely changed to a kind of an orangish red solid looking material. So it's definitely reacted with the Benedicts reagent. The sucrose on the other hand is still staying blue. Benedicts reagent is that color, so it's not reacting with the Benedicts reagent. So there's some information for us. Write that down in your book. And let's get on to the next step. Hey guys, let's continue on with our experiments with carbohydrates. Now we're going to do the hydrolysis of a polysaccharide. I've got 2 test tubes filled with starch. Let me grab them for you. There you go. As you can see, starch is basically more or less a cloudy type suspension. It's just kind of how they look. So as you can see, that's what they look like. So now we're going to add acid to one, water to another, and we're going to do what's called a hydrolysis reaction, or we're going to see what happens when we do a hydrolysis reaction. So let's do that. So here is my 3 molar hydrochloric acid. I'm going to add that to the one labeled acid. I think it says 3 drops. So I'm going to do 3 drops. Actually, it's 5 drops. There we go. So there's the one labeled acid. Give that a little shake. And now I'm going to add some water to the one labeled water. Just going to use a squeeze bottle for that. 5 drops, best I can. There we go. That's about 5 drops. A little more than that, but that's okay. And now I'm going to put them into the, as you can see, they haven't changed much. They really didn't change at all. I'm going to put them into the hot water. And I'm going to let them sit there for about 5 minutes, 5 to 10 minutes. 10 minutes, it says. So there you go. Let's let them sit there for about 10 minutes. Let's crank that up a little more, get the water to boil. All right, guys. See you in 10. All right, guys. It's been about 10 minutes. So let's take our samples out and let them cool down for a few minutes. Okay, guys. Now that our samples have cooled down a little bit, here's what they look like. After heating them, they got a little clearer. There you go. They're more or less comfortable to touch. So now I'm going to do a pH test. I'm going to take a piece of pH paper, which tells you the pH by color. And I want the pH of this acid solution to be above 7. Or to be 7 actually would be ideal, but if it's a little bit above 7, that'll be okay. So let's dip it into here. Now this most definitely, just let me get on frame here. This most definitely should be acidic, right? Because, we added acid to it, right? And there, as you can see, it's red. Red is right around pH 2, just so you know. So this is acidic. So now I'm going to add some sodium hydroxide to counter that, to make the pH come back to about 7. I'm going to add a couple drops. It says in the book to add a ml. I'm just going to add a couple drops. See what happens. 1, 2, 3, 4, 5. How about 5 drops? Probably going to regret not just adding a ml, right? Always follow the instructions, as they say. Sorry, this video seems like it's getting a little dark. Kind of doing these things last minute here, so bear with the production quality. He says like he can make it really good anyway, right? So let's try this again. Here we go. Still acidic, so let's add some more. I just added a boatload, about a half mil. I added about a half mil, to be honest with you. I'm going to stir it up a little bit, get it nice and homogeneous. And let's check. There you go. See, now it's blue. That's basic now. I've went a little higher than pH 7, but that's okay. That's okay. We'll be okay. Now, at this point, we want to get a sample of each one. So now I'm going to take a spot plate. I'm doing the iodine starch test on page 114. I'm going to take some of the one labeled acid. So let's put an A over here, and then we'll put a W here for the acid and base. Let me get my other camera adjusted here, guys, and I'll show you what I'm doing. All right, guys. So now we zoomed in on the spot plate here. I'm going to put a few drops of the acid solution in there. 5 drops. 1, 2, 3, 4, 5 drops of the acid solution. And 5 drops of the water solution. Now this is starch and water, starch and acid. So here's the water. 1, 2, 3, 4, 5. There we go. Now I'm going to add a chemical called iodine, or an iodine solution. Iodine solutions are known to turn black or dark blue in the presence of starch. So this is actually a test for starch. If the solution turns dark blue or dark purple or dark black, we know that there is starch in our solution. So let's try the water one first. There we go. 1 drop, and as you can see, it turned black. So there's definitely starch in the water. So we start it with starch, we added water to it, and we heated it up. So nothing happened, essentially. The starch is still there. Let's see what happens in the acid. Oh, look at that. Look at that. Give it a little stir. Nothing. It does not turn black. So even though we started with starch, we added acid to it, and then we heated it up for 10 minutes, the starch in the acid solution is already gone. Now think about that in terms of food and digestion. When you eat food such as potato chips, for example, potato chips are full of starch. And when you eat them, they go into your stomach, which is filled with acid. And the starch gets digested in the acid, which is kind of what we're mimicking here, just so we're all on the same page. All right, so that's the starch iodine test. So now I'm going to take a brief pause. I'm going to reset up my cameras to do the last step of today's lab, the Benedicts test for glucose. But just bear with me for 1 second, guys, while I reset my cameras. Okay, guys, we're back again. We're going to do the Benedicts test now on the solutions we just heated. Basically, we've learned already that the Benedicts test will turn red in the presence of glucose. We have starch that we heated up in water and acid. We discovered that when heating up a starch in water, nothing happens. The starch remains at the end. When heating up a starch in acid, however, the starch disappears. And what does it disappear to? It becomes glucose. Starches are essentially polymers of glucose. So as we digest the starch with the acid and water at high heat, the starch falls apart to give us numerous glucose molecules. And as we saw with the Benedicts test before, glucose will turn red in the presence of Benedicts solution. So now we're going to test our starch digestion, the acid in starch, to see if there's glucose there. So let's do that experiment right now. I'm going to add a milliliter of Benedicts reagent to each one. So here's my acid. Here's my test tube that's labeled acid. I'm going to add about a milliliter of Benedicts reagent to it. Let me get rid of this bottle here. Get that out of the way too. About a mil. It doesn't have to be too accurate, but about a mil. All right, so put a milliliter in here. And then put that back in the water. The water is nice and hot, so this shouldn't take very long. I'll make sure my other camera's picking that up. All right, very good. That's about a mil. Put it into this is the water one here. Okay, guys, that's the water. Water and starch together that we heated up for 10 minutes to near boiling. All right, let's put that in there. All right. Here we go. Let's just sit and wait now to see what happens. As you can see, the acid one is already a slightly different shade of blue. Hopefully we'll see something soon. Sometimes patience is hard to come by, especially in these days. We have to be patient. I'm sure we'll see a positive result. Or at least an interesting result. All right, guys, we're back again, and as you can see, the glucose is definitely turning brick orange, or brick reddish orange. That's a positive test for glucose, so that's really kind of cool. The acid solution in starch, after heating it for about 10 minutes in near boiling water, the starch digested into glucose molecules. And then the glucose molecules we confirmed using a Benedicts test. The Benedicts test for glucose told me that this is most definitely a digested starch with glucose present. Isn't that kind of cool, guys? All right, guys, thank you for your patience. This is the end of this video, the end of the carbohydrate experiment. Hopefully after this, I'm going to see you all again personally in the lab. I do miss you guys. It's nice to have you guys around. But right now we're in kind of extraordinary times, so we're just doing what we can to prevent the spread of this virus. And thank you guys for all your patience, and thank you for still being here and still trying to learn chemistry as best you can. I'm here for you. Give me a Skype call, give me a call on my phone, email me, do whatever you need to do. We'll get this done together, okay, guys? All right, now with that, I want to wish you all good luck and good chemistry. See you again.